Hello everyone. Today we'll be diving into federated learning, a powerful approach in machine learning that allows data to be processed across devices without sharing the data itself. We'll cover what federated learning is and its key components, how it works, and the different types. We'll also look at its benefits, challenges, as well real world applications. Finally, let me introduce our team, Rajdhani, Surya, Shrutika. We are excited to guiding you through this innovative topic. Let's see.
What is federated learning? Federated learning is a decentralized machine learning approach enabling multiple parties to collaboratively train a shared model while keeping their data local. And participants can train model on their own data and share only model updates with a central aggregator.
The next slide I'm going to talk about is the key components of federated learning. Let's start by understanding the key components of federated learning. Federated learning has two main parts that make it work. The first part is the local models, which each participant, like a device or an organization, trains on its own data. Instead of using all the data in one place, each local model learns independently. Often, algorithms like stochastic gradient descent are used here to adjust and improve the model. The second component is the aggregator. This is a central server that collects updates from all the local models. The local models don't send raw data, they only send updates, which the aggregator combines to improve a global model. Think of this like baking a cake where everyone is responsible for a single ingredient. Only the prepared ingredients go into the final mix. The next slide I'm going to talk about is how federated learning works. Next, let's look at how federated learning works in a few basic steps. First, each device or participant trains a model locally using only its data. Once this training is done, the devices don't send any raw data. Instead, they send only their model updates. In other words, the results of their training process. The second step is aggregation. Here, the central server collects all these updates from the devices and combines them. This aggregation improves the global model to make it more accurate and useful. Finally, the improved model is sent back to the local devices for further training, starting the cycle once again. This process repeats until the global model reaches a desired level of accuracy or performance. The next slide I'm going to talk about is the key components of federated learning. Let's start by understanding the key components of federated learning. Federated learning has two main parts that make it work. The first part is the local models, which each participant, like a device or an organization, trains on its own data. Instead of using all the data in one place, each local model learns independently. Often, algorithms like stochastic gradient descent are used here to adjust and improve the model. The second component is the aggregator. This is a central server that collects updates from all the local models. The local models don't send raw data, they only send updates, which the aggregator combines to improve a global model. Think of this like baking a cake where everyone is responsible for a single ingredient. Only the prepared ingredients go into the final mix.
Now let us see the benefits of federated learning. The benefits of federated learnings are data privacy, diverse data utilization, reduced latency, and the last one is collaboration without data sharing. These are all the benefits of federated learning. Now let us see these one by one. The first one is data privacy. Sensitive data stays local, reduce breach risk and ensuring compliance with the regulations. For example, GDPR and HIPAA. And the second one is diverse data utilization. Leverage data from multiple sources for more robust AI models. And the third one is reduced latency. Local training speeds up model updates as data does not need to be sent to a central server. And the last one is collaborations without data sharing. It helps to institution to improve model collectively while retaining control of their data. Now let us see the challenges of federated learning. The challenges faced by federated learnings are communication overhead, model convergence, security risk, and the last one is implementation complexity. These are all the challenges of federated learning. Now let us see this one by one. The first one is communication overhead. Frequent update can lead to high cost and latency in low bandwidth environment. And the second one is model convergence. Ensuring effective convergence can be difficult with the heterogeneous data distribution. And the third one is security risk. Model updates may expose sensitive information through techniques like model inversion attacks, etc. And the last one is implementation complexity. It means it requires experts in distributed system and machine learning to set up. Now let us see the applications of federated learning. The most familiar applications of federated learnings are healthcare, finance, recommender systems, autonomous vehicles, and the last one is NLP. It stands for natural language processing. These are all the most familiar applications of federated learning. Now let us see this one by one. The first one is healthcare. It securely trains models on sensitive medical data across hospitals or clinics. The second one is finance. Collaborative model training on financial data across banks or institutions. And the third one is recommender system. Personalized recommendation across multiple devices or platforms. And the fourth one is autonomous vehicles. It helps to improve models for navigations and safety. And the last one is natural language processing. It helps to enhanced language models.
Federated learning vs traditional machine learning. When comparing federated learning with traditional machine learning, one of the biggest difference lies in its data location. In traditional machine learning, data from multiple sources is gathered into a central server where the model is trained on all the data combined. This centralization, however, can pose privacy risk as sensitive data from user is stored in one place. Federated learning takes a different approach by keeping data decentralized. Instead of transferring data to a central server, federated learning allows the model to be trained directly on devices where the data is generated, like smartphones or IoT devices, etc. This means the raw data stays on the user's device, which significantly enhances privacy. Another important difference is in communication. Traditional machine learning requires frequent data transfers to keep central server updated. Federated learning, however, only sends model updates, small changes in the model, back to the central server. This greatly reduces the amount of data transmission and further protect user privacy, making federated learning a more privacy-friendly solution overall. Federated learning and cloud computing. Federated learning and cloud computing work hand in hand to create a more efficient and privacy focused approach to machine learning. Federated learning leverages local devices like smartphones and IoT devices to process and update models directly on the device rather than sending data to the central location. Here's where cloud computing comes in. The cloud acts as a central aggregation points, collecting only the model updates from each devices instead of raw data. For example, imagine hundreds of smartphones updating a predictive model based on their local data. These devices process the data locally and send only updates to the cloud. The cloud then aggregates these updates to improve the overall model. This setup combines the strength of both technology. Federated learning reduces data transmission, while cloud computing manages the aggregation efficiently. Future of federated learning. The future of federated learning is promising with advancements in privacy and new integrations. Privacy techniques like differential privacy and secure aggregations are making federated learning even more secure, ensuring that user data remains confidential throughout the process. Another exciting development is the integration with edge computing. As more processing shifts to edge devices like phones and IoT devices, responses can be faster and more private with less reliance on central server. Finally, with the growth of IoT and AI, we are seeing federated learning gain a broader range of applications. As more devices adopt machines like capabilities, federated learning will play a key role in delivering personalized, privacy focused experiences across industries.
In conclusion, federated learning enables privacy preserving machine learning by keeping data local on devices. This approach greatly minimizes data exposure, making it a highly secure model for developing AI models. This technology is essential for industries like healthcare, IoT, and personalization, where protecting data privacy and ensuring security are absolutely necessary. By allowing for secure collaboration without risking sensitive data, federated learning is shaping the future of safe and connected AI in our world. Thank you.